this is changing. Is it changing?
Yeah, we can.
Okay.
Yeah, we hear you.
Okay. Thank you so much. Okay, so I want to welcome everyone to my lecture today. Today we're starting a new chapter that we actually call time series analysis. But before going into time series analysis, four of us want to walk you through what we've been able to do in this course so far. I remember as part of preparation to the course, we actually, I started, well, the course with basic statistics review, just for you to understand some statistical terminologies. And from there, I introduce you to linear regression, where we work on simple linear regression. We also work on multiple linear regression. We work on polynomial regression, regression with multiple nonlinear effects, and so on, like that. Okay. And when there was a transfer, problem, I think I told you that if I really want to know whether my model is doing a fantastic job, what we need to do is to perform what I call regression diagnostics. And of course, after performing regression diagnostic, if everything is good, you can actually move on, trying to use whatever recommendation that you get from your results in policy formulation. But if there's a problem, of course, we also need to go through transformation, or you use different kinds of models. And of course, I remember we also walked through what I call variable selection. I remember variable selection. We actually try to understand what necessary machinery we need to put in place when considering variables into model. So I remember I walk you through all subset selection, all the way to stepwise regression, or to shrinkage, where we talk about lasso regression and the ridge regression. And of course, I also situation where your response variable is not continuous anymore, and if it is a categorical, and you got two levels. Of course, I also walk you through logistic regression. Okay, we use binary logistic regression. I remember I walk you through simple binary logistic, and we also did multiple binary logistic, and I also walk you through how to compare nested models, with logistic regression. And after that, I remember I also walk you through what I call variants of logistic regression. When we talk about variants of logistic regression, there are many. I remember I walk you through Poisson regression, beta regression, multinomial logistic regression, and ordinal logistic regression. So, for Poisson regression, situation where the response variable is a count, okay, we want to study relationship between that particular response variable and some explanatory variable. Of course, we're going to make use of Poisson regression model. And of course, I also walk you through a beta regression model. We use a beta regression model in a situation where the response variable is continuous but is bounded on the range of 0 to 1. Okay, I think I walk you through all of that. Even I also walk you through how to consider different kind of models involving when you have a variable expansion model, all the way to using the log link function and so on, like that. And I remember yesterday I walked you through multinomial logistic regression. In the multinomial logistic regression, we use that situation where the response variable is categorical, but the numbers of levels is more than 2, and they are not ordered. Okay, but situation where they are ordered, we use ordinal logistic regression, statistics is like a story that goes on and on and on. We don't just do what we do. We got a reason why we do what we do. But you know what? Today, in everything that we've been doing, we've never been taking into consideration time. And that is the reason why today we're going to go into time series analysis. But why is it that the idea, from what we've done before cannot be used to fit time series data is because there's going to be violations of independence. Okay, every other regression type that we've been talking about, of course, assumptions of independence has been key. Okay, has been the main key assumption. But when you are dealing with a time component where time is involved, if your explanatory variable is actually time, of automatically going to lead into violations of independence. And that is the reason why we need to consider a brand new statistical model that can actually be used for such. And because of that, I want to welcome you to time series analysis. This is going to be the last chapter in the semester, the last topic. Of course, I have there part 1, part 2, maybe up to part 7. That's all we're just going to be doing all the way to next week. Okay, I want to welcome you to time series analysis, part 1. And this is an introduction. Okay, I'm going to start with this image. Has anybody been to Mississippi National River? Okay, and recreation area. Okay, now if you take a look at this, you know, if you take a look at the year, we want to consider from 2011 to 2018, and we have the record of the numbers of the visitors. In 2011, you saw 99,398. 2012, 106,733. Now, as you can see here, over time, the numbers of visitors varies over time. Okay, and when you take a look at the picture here, okay, this is generating a time plot. We call it a time plot. It is similar to scatter plot. What we've been doing before, the scatter plot is when you have a diagrammatical plotting of a response variable y against an explanatory variable. Okay, yes. But right now, we are plotting, you know, the response variable here, which is the recreation of visitors against time. We're going to call that time plot. And do you know what we want to see? Well, the essence of actually plotting this, the essence of taking record, because I know the same number is not the same number of visitors is not going to come the same year. Okay, I actually want to see, is there going to be an appreciable upward movement or appreciable downward movement? Okay, that's exactly what I want to see. Okay, is the numbers of visitors going to be increasing or is it going to be decreasing? I want to believe the management here really they have interest in that so that they will be able to plan for them. Okay, now this is an example of a time series data. Okay, time series data that we collected over time. Okay, data collected over time. Okay, now for the purpose of analysis, we play with notation a lot. Okay, we're gonna do something right now. Take a look at this guy. I'm trying to say this particular guy. Okay, that is my Y1. Okay, and the other guy is gonna be my Y2. Okay, in a time series analysis, we normally use Y subscript T. Okay, now for 2011, it's going to be Y1. For 2012, it's going to be Y2 all the way. Just wanted to see that. So, okay, now the next thing that I want to talk about is, of course, I just defined time series to you. a sequence of data, that's measure the same thing over time. Why is it the same thing over time? The same thing over time is just numbers of visitors. Okay, but don't forget the same thing over time. The number does not remain the same. Okay, and over an ordered period of time. When we say ordered, this is ordered, is it not? That's ordered, right? 2011, 2012. That's what we mean. Okay, that's what we mean by time series. Okay, now, and of course, I talk about the notation. I say where T is the order time index. Okay, so I think I said that the other time, and we can simply write Y subscript T. Okay, where T can be 1, can be 2, and so on like that. That is actually used to order time. Okay, now is there any question moving forward? Any question at this time? Okay, now I said in linear regression, the subscript y1, 2 up to n and indices for the ID purpose. Remember, ID for the observation, right? But here, they don't necessarily mean the order. The one in the linear regression doesn't necessarily mean the order. Does that make sense? When you collected data over observations, the way the data are presented, it doesn't mean it's ordered. But the one for time is ordered. Does that make sense? Okay. So, and if it is ordered, that was why there's going to be a violations of independence, because you are talking about order here. There's possibility the number that will come in 2012 may depend on the number that come in 2011. Okay. Now, so take a look at that. So like that's why I said in time series, in it, Y1 precede Y2. Y1 preceding Y2 actually means 2011 precede 2012. And 2012 succeed 2011. That's what it means. Okay. Now, let's now look at the outline, like what is important to us that we want to talk about. Okay, we got two concepts in time series analysis that we call the autocorrelation and stationarity. Okay, and I'm also going to talk about the simplest time series cell model that we call white noise. Okay, in this study, I'm going to tell you what is the significance of white noise. What do we mean by white noise? Okay, I'm going to tell you, and I'm also going to tell you what do we mean by autocorrelation, what do we mean by stationarity. Okay, but before I discuss all of that, I actually want to go, I want to go back. So I want to start autocorrelation now. Okay, I want to start from this guy. Okay, mathematically speaking, I'm going to walk you through some basic of mathematical fundamentals. Then I'm now going to tell you the essence in real life. I want to start with the autocorrelation now. Okay, what do we mean by autocorrelation? Okay, now you know what I'm going to do. Autocorrelation means correlation between observations at different moments. Okay, maybe I want to look at the relationship between observations in 2 different years, like relationship between the number that came in 2011 and the number that came in 2012. Now, whenever you see YT, that is talking about the current time. Then you see YT minus 1, that is the immediate past. Please, I need you to pay attention to this now. YT against YT minus 1, maybe I need 2012 against 2011, or 2013 against 2012, or 2024 against 2023. Does that make sense? Now, how many lag apart? That's a 1 lag apart. 1 lag apart. When I talk about lag, that depends on the unit of time. It could be year, it could be month, it could be quarter. For example, if I'm talking about year now, and I'm actually want to talk about a correlation at lag 1. For year, maybe I'm trying to look at what happened, relationship between 2012 and 2011, 2013 and 2012, 2014 and 2013. Does that make sense now? That is 1 lag apart. We can also have two lag apart, can have three lag apart, and so on like that. Okay. Now, when I actually plot that, okay, if I plot that right now, you're actually going to see this. Take a look at, so this is what we call the autocorrelation plots. Okay. What you're actually seeing right now, okay, just like what I said, okay, give me 1 second. Okay, the whole thing is going to start from Y1, Y2, Y2, Y3, Y3, Y4, Y4, Y5, Y6, Y7, Y7, Y8. Does that make sense? You are looking at the relationship between two different movements, and the lag is one. So this is what I mean. This is that correlation between YT and YT minus 1. What is the lag apart is 1. So that's a lag 1. Okay? That's what we mean. Okay. Now, uh, of course, we have a code in R that will enable us. You know what this guy is telling me now? He's trying to tell me correlation between YT and YT minus 1 is 0.65. When I say YT and YT minus 1 is the same for all, whether for Y2 and Y1, or for Y3 and Y2, or for Y4 and Y3, up to Y8 and Y7. That's what we call the autocorrelation, okay, at lag 1. Now, you know the next thing now? What is this? You know what that guy is saying? Is there a difference between them? Can you tell me? Can somebody tell me? Look at this. Look at the other one. He said, what is the correlation for YT minus 1, comma YT minus 2? Is there any difference between them? No. Because my own, if I'm considering Y7 and Y8 and Y7, your own may be Y7 and Y6. It's still the same. So what I'm trying to say, YT minus 1 and YT minus 2 is the same. Why are they the same? You consider the lag they have apart. The lag they have apart is 1. Does that make sense? Okay. Now, so which I said, the estimated autocorrelation at lag 1. Or for this data set, all estimated autocorrelation at lag 1 is going to be the same. And that is that 0.65. Like I said, when you have data set, I'm actually going to, of course, in the lab, the MIT is going to show you how we use, but since we started time series today, what is going to show you in the lab tomorrow is never going to be on time series. It's going to be on Poisson regression, multinomial logistic regression, ordinal logistic regression, and the beta regression. Okay. Now, I want to go into this now. Okay. If I talk about Google stock price, but let me first tell you this. We got so many examples for time series. My time, it could be the numbers of visitors, that visit our bank weekly. It could be amount of money you make every week. Provided their data collected over time, they are times series data. Now we want to have an example here about Google stock price. When you take a look at the stock price, keep changing, right? Because we live in a stochastic environment, we expect things to be changing. Okay, now we want to talk about, for instance, I want to look at the relationship between Google stock price today versus the day before yesterday. I'm not talking about yesterday now. Today and a day before yesterday. That would be this guy. Do you see that? How many lag apart? That would be two lag apart. Okay. If I want to focus on where am I plotting this? Because I want to be able to relate. I want to see the role play by the Google stock price a day before. What is the contribution of that to the to what the Google price is going to be today? Okay, here you are looking at the autocorrelation at lag 2. Okay, now, which is that? Take a look at that. So when I have the data set right now, the estimated autocorrelation at lag 2 is actually going to be 0.912. So it's 0. The correlation lies between -1 and 1. The moment you have a 0.912, that's a lot. You get what I mean? That's a very strong one. Okay, take a look at that. So what this guy is trying to tell me now is that there is a very strong connection between the Google stock price today and a day before. Is there any question? That's what this guy is telling me now. Okay, now, which is what we call the estimated autocorrelation at lag 2. Okay, now I want to go into stationarity right now. Okay, I want to go into stationarity right now. Let me tell you this. If I want to work, every statistical model has assumptions. I'm going to say that again. Every statistical model has assumptions. Okay, what make a model to be great is when there's no violation of assumption. Okay, one of the assumptions in time series model is stationarity. I'm going to say that again. One of the assumption in time series model is stationarity. Let me tell you this. What do we mean by stationarity? Do you know that imagine a world where we're actually gonna be happy all the time. We're gonna be celebrating all the time. Every day things is gonna be the same. I don't think that kind of world exists, because we live in a stochastic environment. We live in a probability space. We expect variation. But despite that, if we want to use a time series model, we need to have an assumption of stability first. Does that make sense? It's just like you go into a court. Okay, court is going to assume what? A suspect is innocent unless proven guilty by law. Does that make sense? Okay, now, what do we mean by stationarity? Please, I need you to take note of this. Stationarity assumption implies that the mean has to be constant over time. Like things remain the same over time, mean being the same over time. Okay, variance, the same over time. Okay, mean the same over time, variance the same over time. And let me now tell you this. When we talk about autocorrelation, take a look at this. Autocorrelation at lag 1, okay, they will be the same, all true. I just demonstrated that to you the other time. The correlation of Y1, Y2 must be the same as Y2, Y3, must be the same as Y4, Y5. The moment they are lag, they are the same lag apart, they are going to have the same value. Does that make sense? Now, if the same thing applicable to lag 2, and you know what? If I'm talking about lag 1, we're actually going to represent as row 1. You know the meaning? Row 1 is a notation for autocorrelation at lag 1. Whenever you see that notation, it actually means autocorrelation at lag 1. Okay, whenever you see the second one, okay, whenever you see the second one, that's an autocorrelation at lag 2. Look at that, at lag 2, Y1, Y3, Y2, Y4, Y3, Y5, and so on. When you are considering the autocorrelation of two variables that are two lag apart. Now, you know what I want to do now? I'm actually going to generalize. I think there's a mistake here. This is supposed to be Roy K. Okay, if I want to generalize now, okay, I want to generalize, okay, generalize it now. Okay, take a look at this guy. How many lag apart? Y1 and Y1 plus K. That's a K lag apart, right? K lag apart. How are you going to know the lag apart? You can do 1 plus K minus 1. What is 1 plus K minus 1? That's going to be K, right? If you look at the other one, 2 plus K minus 2. Okay, that's going to be Roy K. Is there any question here about the mean? About I said the assumption is that mean has to be the same over time. Okay, and the variance has to be the same over time. These are just assumptions. Okay, and as for correlation, okay, I'm actually going to tell you the implication of this when we get to a model. Okay, but these are the assumptions. Now, identify. Now, let me tell you this. How, when we have a data set and they are time series data set, how can we identify non-stationarity? I just told you right now, identify non-stationarity is for you to be able to see that mean changes. Non-stationarity. For stationarity, what happened? Mean have to be the same over time, right? Variance have to be the same over time. Not only that, the autocorrelation for all lag 1 have to be the same. For all lag 2 have to be the same for up to all lag K. Now, you know what? If you plot a series, take a look at this. Okay. Now, what do you see here? This is changing over time. Look at that. You plotted this against time. What is happening? That's a fluctuations, right? That's a violation. Well, and that was why I said this time series plot show that variance is not constant. You can see, is the variance constant? Because the variation here is different from the variation here. Okay, the variance is not constant over time. Look at that. Okay, now that actually seems that the variance is increasing over time. Okay, I want you to take note of that. Therefore, that the time series is not stationary. Let me tell you this, when you're working with any time series data, we need to first investigate for stationary. The moment it is not stationary, then we need to, we also have transformation in time series, but we don't call it transformation. We're still going to talk about it. We call it differencing. It's part of the topic we're going to do. Okay. In statistics, we can never be cornered. Whenever there's a problem, we actually understand statistical way out. Okay, now because of that, the time series here is not stationary. What of in exam, I gave you a picture and I said, comment on the stationarity of this particular graph. Okay, this is not, the variance here is changing over time. Then that's a violation. Now, another one. Oh my God, what is happening here? The variance is the same, but what is changing? The mean. Good job. The mean is changing, which is a violation. And that was why I said the time series plots indicate that the mean is not constant for all t. What happened? The mean appears to be up, appears to go up. Look at that. That's good. That's a violation. How am I going to know? I actually need to plot the series against time. We call that a time plot. Does that make sense? Okay. Now, what have we been doing? We've been identifying non-stationarity. Okay. Now, because of that, we're going to say the time series is not stationary. Okay. But let me tell you this. Sometimes, don't be deceived. You remember one time I talked about in regression modeling situation, at times our residual plot could mislead us. At times, I told you. Now, sometimes the time series plot, time series plot is what I call time plot that I showed you the other time. Now, could mislead us. Now, for example, you know why it's going to mislead us? It may depend on the number of observations you take. Don't forget, even when we're dealing with the residual plot the other time, I told you, depending on the number of observations you have, there's possibility it could mislead us. Now, I said, for example, the following time series is stationary according to the population model. Let me tell you this. Before plotting the series, we already have a model that we generated the data, and we already know that it should be stationary based on what we plug in. But you're going to see something. And I said, however, the time series plot suggests an increasing mean. Now, this is what we put into consideration. Take a look at this. Well, what do we call this? This is a time series model. Now, do you know what this time series model is doing? We are relating the current time to the immediate past. You know what YT means? The YT means, oh, the amount that we make in our store today. YT minus 1, oh, the amount that we made in our store yesterday, if your unit of time is day. Does that make sense? You are relating the current to the immediate past. Does that make sense? So we actually use our days to simulate our data. But let me tell you this. I'm still going to talk about some stuff. You know, if you take a look at this side, that's a deterministic aspect of the time series model. Then we take a look at WT. That is a random part. Every statistical model must have a random part. But in time series, we don't say this. We normally call it, that random part, we call it white noise. We want it to be a white noise. I'm going to tell you the meaning of white noise. Okay, now when I'm still coming to the model, okay, now we simulated. If you take a look at the data, we use this to simulate our data. We use that to simulate. Okay, next week you're still gonna work it out to simulate our, you know, you're gonna see a lot of coding now. Now, when we are simulating this data, okay, we simulate we simulating it with, you know, we put into consideration that WT, the noise, that WT that we've got a random part, follow normal with the mean zero and a constant variance 0.19. We are already assuming constant mean, constant variance. Okay. Now, but you know what? Is this giving us that? Is what we plotted giving us that impression? No. Okay. And that was why I said here. I said the time series has 50 observation. This one has 50. You can see 0, you can see 50, right? Okay. Now, despite the fact that when we simulate our data set, okay, we actually simulating from, you know, we are already assuming a constant variance and constant mean, but this is not giving us that picture. And the reason why it's not giving us the picture is because the observation is not large enough. And you know what? When we now try to look at that, we go to 100 and 1000, you know, initially, how many data points? 50, right? Now, we now increase the number to 100. We want to plot again and see. Oh my God, what has happened now? Stability. Do you see some form of stability? You see stability here, and that is so glaring here. Okay, you know, it's like something that is moving up, that's going moving. You get to a point, then it now becomes stable. Can you see that? Okay, now that was why I said here. Take a look at it. I said, once we increase the number of observation, we can see that the time series slowly converges. Okay, converges to 20. Okay, slowly, because if you take a look at it too, that convergence starts at time equal to 20, converges to 20, and they stay at that value with only, we're not going to have a perfect stability. Don't forget that, but it stay in that very region with only small fluctuations. Does that make sense? Now, the mean and the variance seem to be constant for time greater than 40. Can you see that now? Okay, so this is it. At times, when you, depending on the number of observations that you're considering in time, okay, it could be stable or not. And don't be misled. Even though you are simulating from a model where you know, there's no any violation, you've put into consideration the constant variance, the constant mean. If you are working with a small sample, when you generate a plot, it could mislead you. Okay, now, and I said the increasing trend we see at the beginning is due to unfortunate starting point, because we start from zero. That was why. And it takes about 40 time period for the time series to climb out that valley. okay, to converges to a particular point with small fluctuations. Okay, now I'm now going to say, therefore, even though YT is stationary, the first part of the plot misled us to believe that it was not stationary. Therefore, we need to be very, very careful. And that is the reason why statistical analysis, before we can have a model that is not going to mislead, we need to consider a sufficiently large sample. But that is not, we have a way to. So I want to come back here now. I particularly want to talk about time series model, and I want to talk about white noise. Okay, now I needed to take a look at this. If this is a model, it's a time series model. Okay, this time series model is called autoregressive model of order 1. Autoregressive model, AR means, when you say autoregressive, what is it meaning? You're going backward. You're relating. Order 1 means relating what happened now with what happened to the immediate past. What happened now is YT. Immediate past is YT minus 1. Does that make sense? Okay, now in the model that we have considering right now, okay, that part has a name. That is a deterministic part of a model. In signal processing, we call that signal. Okay, in the analysis of communication, they normally want a situation where they're going to filter out what? Noise. Okay, therefore WT is a noise. WT is a noise. That's why the random part of a time series model is a noise. And what do we want to do? We want to filter out the noise. Noise here is the error in linear regression that we said we want to minimize. Does that make sense? Therefore, what happened today? Your YT is contaminated with signal and a noise. And what we now want to do in the analysis, if we really want to understand this scenario, what we're going to do is ability to filter out the noise. Does that make sense? Okay. Now, which I said, similar to linear regression. Of course, is that not similar to linear regression? Okay. Now, similar to linear regression, that part, okay, and that part in linear regression, okay, this part is this part in the simple linear regression. Why that part is that part? Does that make sense? Okay. Now, I'm actually going to move right now. Let's say, for instance, I want to talk about, let's say, why this guy is the model for the daily revenue from ice cream store. What do we think we're trying to do? We are relating the revenue that we made today in our store selling ice cream. We are relating that to the revenue for yesterday. Does that make sense? That is when the units of time is day. The unit of time can be in months. The unit of time can be in year. Does that make sense? And the WT is any other thing that could have effects on what we make today. That economists at times they call WT shock on the system. It could be any other thing that you do that make you to sell. Does that make sense? Now, take a look at this guy. Do you see that? Let's say, for instance, by the time we multiply, is 0.97 here. We are assuming that to be similar to regression coefficient. We are assuming that to be a contribution. What yesterday contribute to today sales. Okay, and if I know today's days, if I multiply by that is 100, and noise is if the noise is 2, because there's always going to be a contribution from noise. And of course, what do you expect the YT to be? That would be 102. Does that make sense? But that is not what I want to explain now. I'm still gonna, but you know what I want to deal with now. This is where I need you to pay attention. I want to explain something which is very, very crucial. Let me tell you this. In any time series model, we have a noise, right? A random part. We want the noise to be a white noise. What do we mean by white noise? White noise means that very noise we've been able, it behaves well. Behaving well means we've succeeded in filtering out that noise, because it's only you'll be able to get signal, you'll be able to get the deterministic part, you'll be able to get your pattern, well, your pattern or the trend, if you have succeeded in filtering out the noise. Now, because of that, I want to talk about white noise model first. White noise model. Now, this is a white noise model. White noise model is the simplest model in time series analysis. Do you see? We're only relating YT to noise. C is a constant. It means we're not relating YT to previous days. Okay? This is more or less like the simplest model in linear regression. You know the simplest model in linear regression? Intercept model. You remember? But in time series, why do we want to investigate white noise model? Let me tell you this. There are two things. White noise model is significant for two things. Okay? For benchmark, is significance for benchmark comparison. Okay, benchmark comparison. Okay, please, I need you to pay attention. You need this all the way. Benchmark comparisons. Then two, model diagnostics. Model diagnostics. Okay. Now, I need you to listen now. Why do we need a white noise model in time series? Number one, I said benchmark comparison. What do I mean by benchmark comparison? It enables us to investigate the presence of trend. Trend. You know what I mean? Trend. Like, are we going to have increasing or decreasing, or the pattern? Okay. That is so situation where if your model is a white noise, if your model is a white noise, you know the meaning? If your model is a white noise, then it means there is no signal, there's no pattern, there's no trend. Does that make sense? If your model is a white noise. Does that make sense now? And you know what that means? That is very, very crucial. That explains the fundamental reason why I mean, that will enable us to understand randomness and unpredictability in scientific field and engineering field. Does that make sense? So if your model is white noise, if your model is a white noise model, it means we cannot make a prediction. There's no pattern. That's what it means. Does that make sense now? So now I just told you the number one reason, benchmark comparison. Number two reason is model diagnostics. Now, let me tell you this. When we fit a time series model, we expect the error in the model to be a white noise. You know how am I going to know? If it's a white noise, I'm going to know? The mean should be constant over time. The variance should be constant over time. The autocorrelation should be zero. Does that make sense? That is how I'm going to know. So mean should be constant over time. The variance should be constant over time. Autocorrelation between, because let me tell you this, if the autocorrelation between, when I say autocorrelation means zero, means autocorrelation for errors. If the error today, okay, if I look at the correlation between error today and error yesterday, correlation should be zero. What does that mean? If the correlation is zero, it means it's a white noise. It means we don't expect relationship between the errors at different periods. Does that make sense? And that is exactly what we want. Okay. Now, I just show you now take a look at this. WT is a white noise, and WT follow normal distribution with the mean zero, and that is the variance, sigma squared. Now, let's look at two time series below that we generate. When you have this guy, your module is a WT, means your module is a white noise module. What did I say about white noise module? A white noise module cannot be used for prediction. Okay? But I need you to take a look at it. If your module is entirely white noise, then your module is bad. I'm going to say that again. If your module is entirely white noise, it means there is no pattern, there is no trend. You cannot use the module to predict. But if the random part in your module is white noise, then your module is going to do a great job. Does that make sense? I'm going to say that again. If your module is entirely white noise, then you don't have a good module. No pattern, you can't use it to make a prediction. But if the random part in your module is a white noise, then that now indicates that your module has done a great job in identifying the pattern. Does that make sense? Okay. Now you know what I want to do now. I want to generate a series of data, and for module that is a white noise for you to see. And of course, I want to generate from normal distribution with a mean 0, variance 1. Okay. Now, the first one, this is the first one, the simulated, and this is the second one. Can you see that? That is the way it's going to look at that. At the end of the day, you're going to see the mean is going to be on average going to be at 0. Look at that. Okay. And the variance is actually, so that is a white noise. So revisiting the white noise model. Okay. The autocorrelation at lag 1, lag 2, lag 3 for white noise model. Can somebody tell me? What is going to be the autocorrelation at lag 1 for white noise? Lag 2, lag 3 to lag K is going to be 0 under assumption. Okay? It's 0 under assumption. Now, take a look at this. Look at this. And look at this. You're going to see something now. Now, take a look at that. The first one for lag 1, lag 2, lag 3. What happened? They will never be correlated. That is for the white noise. For white noise, no connection between the Google stock price today and yesterday, today and the day before, and so on like that. That's what we mean. No autocorrelation. And that's exactly what we want. And if there is no correlation, you know what happened? They are independent. Does that make sense? Okay, let me show you the last example before I go. This is the last page. Let's say, for instance, suppose the module for Kazim daily sleeping hours, my sleeping hours now, let's say the module is this. You know what I'm trying to say? I said the module is a white noise. If the module is a white noise, you know the meaning? You cannot predict my sleeping hours. That is the meaning. So YT equal to WT plus A. If I simulate, I'm actually going to have this guy here. Okay, do you see that? And what am I trying to say? If I want to find this, if I know that YT equal to WT plus 8, And I want to find the expected value of YT. Expected value of YT is going to be this. Expectation times this. Expected value of a constant is that. What is the expected value of WT? 0. How do you know? Because it's because it's defined here. Look at that. When you see that line, the first value is the mean, which is the expected value of WT. The second value is the variance. Okay, so what this guy is trying to say is that expected value of WT is 0. Okay, and the variance, sorry that I'm going to use just 2 minutes, so we're on the last page. The variance of WT equal to 1, based on that specification. Now, you know what you're trying to tell the world? On average, my sleeping hour is that. That's what I'm trying. That's what you're based on that model. Okay. Now take a look at this. What about the variance? Let's look at the variance. Variance of WT. Variance of a random variable plus that is just going to be variance of WT, because the variance of a constant is 0. And what is the variance of WT you've been given is 1. Do you see that? Okay. Now, if I look at the autocorrelation, because of the fact that, this guy here, rho 1 means autocorrelation between two periods that are 1 lag apart. Whether they are 1 lag apart or 2 lag apart or whatever lag apart, it's always going to be 0 for white noise model. Okay, this one equal to 0 means this period and the other period are not related. Okay, if they are not related, then I cannot make a prediction. So what I've demonstrated to you is what we call a white noise model. This is a situation where the model is entirely white noise. When a model is entirely white noise, it doesn't make sense. It means you cannot make a prediction. But what is the essence of white noise? The essence of white noise is for us to have a benchmark comparison and for diagnostics. Now, the diagnostic is if the random part of my model is white noise, just if I have a model and the random part is a white noise, it's a good model. But if the model is entirely white noise, it's not a good model. That model, it means you are not relating what happened at a current time t to previously existing past. Then it means there's no connection between period. Then you cannot use it to make a prediction. This is where I'm going to stop. Is there any question? Okay, make sure you all stay safe and have a lovely. Okay, the TA is going to walk you through lab tomorrow. The exam is going to be posted starting at 12 noon all the way to 11:59 p.m. on Sunday. You can decide to start at any time you want. Okay, so but the moment you click on start, your time is going to be running out. So make sure you plan wisely. It is only when you are ready to start that you should start. But the exam is going to be left open all the way from 12 noon tomorrow to 11:59 p.m. on Sunday. Okay. And of course, the TA is going to walk you through, lab tomorrow. He's going to walk you through what we did and also going to walk you through the midtime 2 practice questions that are uploaded. Okay. So, and of course, do whatever that will make you to succeed in the exam. It's an open book, but you cannot, seek for assistance from your colleague, and you cannot provide assistance. And when you join the Zoom with your video on, and make sure you are muted whenever you want to start. Reason why you need to be muted, there's possibility when you join the Zoom, you could meet another student in the Zoom, and make sure you are muted. And when you meet another student in the Zoom, no communication, because I got a way to track all of that. I wish you very best of luck. Make sure you all stay safe and have a lovely weekend. Bye for now, everyone. Okay,
Thank
so
you.
if you any question?
No, thank you. Have a good weekend.
You too. Bye for now.